For 40 years, a spacecraft called Voyager 2 held the only close-up data humanity had of Uranus. It flew past the planet once in January 1986, took its pictures, recorded its readings, and left. No other mission has been back since. Not one. And for decades, scientists worked with what that single flyby gave them, assuming it was the full picture. It wasn't. In 2025 and into 2026, the James Webb Space Telescope quietly proved that Voyager 2 missed things right in front of it. A moon hiding in plain sight, and a planetary mystery that took almost 40 years to even recognize as a mystery. This is the story of what Webb found, why Voyager 2 never stood a chance of finding it, and what it means for how we understand one of the strangest planets in our solar system. Let's start with the basics, because Uranus doesn't get enough attention, and that's part of why this story matters. Uranus is the seventh planet from the Sun, an ice giant made mostly of water, ammonia, and methane, surrounding a small rocky core. It's famous for one strange trait. It spins almost completely on its side. While every other planet in the solar system rotates more or less upright, Uranus is tilted about 98 degrees. So it essentially rolls around the Sun like a ball instead of spinning like a top. Nobody knows for certain why. The leading theory is that something enormous, maybe an object the size of Earth, slammed into it billions of years ago and knocked it over. That single event may explain not just the tilt, but the strange arrangement of its rings and moons too. Uranus was discovered by William Herschel in 1781, making it the first planet found using a telescope rather than the naked eye. For the next 2 centuries, it stayed a distant, blurry dot in our sky. Nobody had detailed images. Nobody had close-up data. That changed briefly in January 1986 when NASA's Voyager 2 spacecraft became the only human-made object to ever fly past Uranus. Voyager 2 had launched back in 1977, part of a mission designed to take advantage of a rare alignment of the outer planets that happens only once every 175 years. The spacecraft used gravity assist to sling itself from Jupiter to Saturn to Uranus and eventually Neptune, using each planet's gravity like a slingshot to reach the next. By the time it reached Uranus, it had already been traveling for almost 9 years. The flyby itself lasted just a matter of hours. In that short window, Voyager 2 gathered as much data as it possibly could. It photographed the planet and its rings, discovered 10 new moons, found 2 new rings that hadn't been seen from Earth, and measured this planet's magnetic field and radiation belts. At the time, this was groundbreaking. Before Voyager 2, Uranus had only 15 known moons, all named after characters from Shakespeare and Alexander Pope, a naming tradition that makes Uranus's moon system genuinely unique in the solar system. Voyager 2's discoveries nearly doubled that count in a single pass. But here's the thing people often forget. A single flyby, no matter how good the instruments, is not the same as a full survey. Voyager 2 had hours, not months or years, to observe an entire planetary system. It could only capture what was bright enough, big enough, or positioned well enough to be seen in that narrow window. Anything smaller, fainter, or badly placed at that exact moment would simply be missed. And that's exactly what happened. Twice. In 2 very different ways. The first miss involves radiation. When Voyager 2 flew past Uranus, its instruments recorded radiation belts around the planet that were far more intense than anyone expected. This was strange, but at the time, scientists didn't have a way to explain it. And they didn't have a way to check it either, since there was no other data to compare it to. So for almost 40 years, this reading just sat there. An anomaly, a footnote, a piece of data nobody could fully explain. Uranus's radiation environment was assumed to simply be unusually strong, full stop. It became one of those quiet mysteries in planetary science, not dramatic enough to dominate headlines, but nagging enough that researchers kept coming back to it. Then, more recent research revisited that old data using significantly more advanced modeling and a broader understanding of how the sun's activity affects planetary environments. The new conclusion was surprising. It wasn't that Uranus's radiation belts are always that intense, it's that Voyager 2 happened to fly past during an extremely rare solar wind event, one that temporarily flooded the planet's radiation belts with a massive burst of extra energy. In other words, Voyager 2 didn't capture Uranus as it normally is. It captured Uranus in the middle of what researchers describe as something like a cosmic perfect storm, an unusual spike caused by a rare compression of the solar wind reaching the outer solar system. Similar storms have been observed affecting Earth's own radiation environment, dramatically boosting radiation levels for a period of time before things settle back down. This is a big deal, because it means scientists had been building models of Uranus's magnetic field and radiation environment based on data that may not represent typical conditions at all. It's a little like trying to understand a country's average weather by visiting during the 1 week a decade when a massive storm rolls through and then assuming that's just what the weather is always like there. For almost 40 years, that assumption stood simply because nobody had a second data point to compare it against. This new research doesn't just correct an old error. It reshapes how scientists think about Uranus's magnetosphere altogether, and it strengthens the case that has been building for years. Uranus deserves another dedicated mission, one that can observe the planet over time instead of catching a single fleeting snapshot. That's the first thing Voyager 2 missed, or more precisely, misrepresented, simply because of when it happened to arrive. But the second miss is even more direct, and it's the one most people are talking about right now. Voyager 2 didn't just misread Uranus's radiation, it flew straight past one of its moons without ever knowing it was there. In 2025, a team of astronomers led by Dr. Mariameh El-Motamid at the Southwest Research Institute used the James Webb Space Telescope to take an extended look at the Uranus system. On February 2, 2025, Webb's near-infrared camera, known as NIRCam, captured a series of 10 long-exposure images, each lasting 40 minutes. Long exposures like that allow a telescope to gather much more light than a quick snapshot, which makes it possible to pick out extremely faint objects that would otherwise be completely invisible. Buried in that data, the team spotted something new, a tiny, previously unknown moon orbiting Uranus, given the temporary designation S22FU1. This moon is small, really small. Scientists estimate it's only about 6 miles or 10 kilometers across. To put that into perspective, that's roughly the size of a small town, not a planet-scale object. It orbits Uranus at a distance of about 35,000 miles from the planet's center, tucked between two other moons called Ophelia and Bianca, right in the same general region as the planet's ring system. Its discovery brought Uranus's total known moon count up to 29. Here's why this matters so much. This moon was always there. It didn't just appear, it has presumably been orbiting Uranus for a very long time, possibly billions of years, sitting quietly in that same spot the entire time Voyager 2 flew past in 1986. It was there when Voyager 2's cameras were pointed directly at that region of the Uranus system. And Voyager 2 never saw it. Not because the spacecraft's instruments were bad, but because the moon is simply too small and too faint. And it was sitting right next to something incredibly bright, the rings and the planet itself. One researcher on the Discovery team compared the challenge to staring directly into a car's headlights and trying to spot a fly buzzing nearby. The brightness of the nearby object essentially drowns out anything faint and small close to it. Voyager 2's cameras in 1986 simply weren't sensitive enough to pull a 6-mile-wide object out of that kind of glare. Even the Hubble Space Telescope, which has spent decades studying Uranus from Earth orbit, never caught it either. James Webb could, because Webb was built for exactly this kind of challenge. It observes primarily in infrared light, using a mirror over 21 feet across, more than 2.5 times larger than Hubble's mirror, giving it dramatically more light-gathering power. Combined with incredibly sensitive detectors and the ability to take long, stacked exposures without the interference of Earth's atmosphere, Webb can pick out objects that are both extremely faint and sitting close to something extremely bright, which is precisely the situation with small inner moons near a planet's rings. It's not that Voyager 2's mission failed. It's that Webb represents a genuine generational leap in what's possible, allowing scientists nearly 4 decades later to go back and find something that had been hiding in plain sight the entire time. Once the discovery was confirmed, the scientific community reacted with real excitement, and not just because of the moon itself, but because of what it suggests about everything we still don't know. According to researchers involved with the discovery, no other planet in the solar system has as many small inner moons as Uranus does, and this newly found object is fainter and smaller than any of the previously known ones in that same region. That's an important detail, because it strongly hints that this isn't the last one. If this moon, at just 6 miles across, could stay hidden for almost 40 years, despite multiple space missions and telescopes studying the area, there's a real possibility that more objects like it are still out there, simply too small and too faint for even Webb's current observations to catch in a single pass. This new moon will officially be named at some point by the International Astronomical Union, following the long-standing tradition of naming Uranus's moons after characters from the works of William Shakespeare, alongside a few from Alexander Pope. Uranus's moon system includes names like Titania, Oberon, Miranda, Puck, and Desdemona, drawing directly from plays like A Midsummer Night's Dream and The Tempest. Until an official name is chosen, the moon remains known simply by its provisional scientific designation. Scientists are especially interested in what this moon, and others that share its neighborhood, can tell them about the broader history of the Uranus system. The region near Uranus's inner rings is thought to be closely connected to how those rings themselves formed and behave. Small moons like this one may play a role in shaping, maintaining, or even slowly destabilizing the rings through their gravitational influence over long periods of time. Understanding these tiny bodies could help explain why Uranus's rings look the way they do, how stable that system really is, and what kind of turbulent history the region has gone through. Researchers have pointed out that Uranus's inner moon and ring system appears to be tied together in ways that suggest a genuinely chaotic past, possibly linked back to that same giant impact theory that may explain the planet's extreme sideways tilt in the first place. There's also something genuinely exciting about the timing of all this. James Webb wasn't built specifically to study Uranus. Its primary mission goals center on deep space, on distant galaxies, early star formation, and detailed atmospheric studies of exoplanets orbiting other stars. Yet, in its downtime, pointed toward our own solar system, it managed to make a discovery in our own cosmic backyard that had eluded every other instrument for 4 decades. That says a lot about just how capable this telescope really is, and it hints at what else it might quietly uncover as it continues its mission, simply by turning its incredibly sensitive instruments toward familiar places and looking more carefully than anyone ever has before. So where does this leave Uranus, and where does it leave us? For now, the 7th planet still holds its title as one of the least explored destinations in our solar system, visited exactly once, decades ago, by a single flyby. We now know that flyby caught the planet during an unusually intense radiation storm, distorting our baseline understanding of its magnetic environment for almost 40 years. We also know that hiding just outside the rings that Voyager 2 photographed, a 6-mile-wide moon sat completely undetected, only revealed decades later by a telescope built for entirely different purposes, using long-exposure infrared imaging that simply didn't exist in 1986. And we know that scientists studying this small moon believe it likely isn't the last hidden object out there. There may be more faint, tiny worlds tucked into Uranus's ring system, waiting for the next generation of even more sensitive instruments, or a long-awaited dedicated mission, to finally bring them into view. Let's slow down for a moment and really unpack why a single flyby is such a limited way to study an entire planetary system, because this is the detail that makes both of these discoveries make sense. When Voyager 2 approached Uranus, it wasn't slowing down to orbit. It was moving fast, using the planet's gravity to bend its path and pick up speed on the way to its next destination, Neptune. That meant the spacecraft had one continuous pass through the system, with a window of closest approach lasting only a matter of hours. During that window, its cameras and instruments had to capture as much as physically possible. Images of the planet's cloud tops, measurements of its magnetic field, readings of charged particles in its radiation belts, and photographs of every moon and ring segment bright enough to register on its sensors. There was no second chance to go back and check a blurry image, no way to wait a few months and see if conditions changed, and no ability to point the cameras at a suspicious dark patch near the rings for a longer exposure. Whatever Voyager 2 captured in those few hours became, by necessity, the baseline for everything scientists believed about Uranus for the next several decades. Compare that to how the James Webb Space Telescope operates. Webb sits at a stable point in space known as the second Lagrange point, roughly 1 million miles from Earth, where it can maintain a consistent, shielded view of deep space without the interference of sunlight bouncing off our planet or the scattering effects of Earth's atmosphere. From that vantage point, astronomers can schedule observations of Uranus whenever they want, for as long as they need, using long-exposure imaging techniques that simply were not possible for a spacecraft racing past the planet at high speed. The 10 40-minute exposures that captured the new moon in February 2025 add up to nearly 7 hours of dedicated observing time, spent studying a single, narrow region of space around Uranus. Voyager 2 never had that luxury. It had one shot, moving quickly, and with instruments from the late 1970s, built years before it even launched. This difference in observing strategy explains almost everything about why these two discoveries happened when they did, and not sooner. It's not a story about one mission failing and another succeeding. It's a story about two fundamentally different kinds of science. A flyby, built for speed and broad coverage, versus a stationary patient observatory, built for depth and sensitivity. Both approaches matter. Voyager 2 could never have been redesigned to sit around Uranus for months, and Webb could never physically fly through the system to measure its magnetic field directly. They complement each other across a 40-year gap, and together, they're finally starting to paint a picture closer to the truth. It's also worth remembering just how remarkable it is that Voyager 2 got to Uranus at all. The mission relied on a rare planetary alignment that lines up the outer planets in a way that allows a single spacecraft to visit several of them using gravity assists, saving enormous amounts of fuel and time. This alignment happens roughly once every 175 years. Miss that window, and the next opportunity wouldn't come until sometime in the 2150s. Voyager 2 launched in 1977, specifically to take advantage of this alignment, and by the time it reached Uranus in January 1986, it had already flown past Jupiter and Saturn, using each planet's gravity to bend its trajectory further outward. After Uranus, it continued on to Neptune, becoming the only spacecraft in history to visit all 4 of the solar system's giant planets. That's an extraordinary engineering achievement, and it's part of why the data from that mission has been treated with such weight for so long. It wasn't just good data. For most practical purposes, it was the only data available, and it likely will remain the only direct spacecraft data for a very long time, since there is currently no funded mission scheduled to send another spacecraft to Uranus in the near future. That's exactly why these new findings matter so much to the scientific community, and why they keep surfacing in serious discussions about future mission priorities. Groups of planetary scientists have spent years arguing that Uranus, along with Neptune, represents one of the biggest remaining gaps in our exploration of the solar system. Every other major type of planet, rocky worlds like Mars, gas giants like Jupiter and Saturn, has had multiple dedicated missions, orbiters, and even landers. The ice giants have had exactly one flyby each decades ago and nothing since. Proposals for a dedicated Uranus orbiter and atmospheric probe have circulated for years, aiming to do for Uranus what missions like Cassini did for Saturn. Spend years in orbit, studying the planet's atmosphere, magnetic field, rings and moons in continuous detail rather than a single rushed pass. These new discoveries, both the radiation storm revelation and the hidden moon, are frequently cited as fresh evidence supporting exactly that kind of mission, because they demonstrate just how much can still be misunderstood or missed entirely without sustained close-up observation. Now, let's return to the moon itself for a moment, because there's more worth understanding about what makes an object like S2025U1 so difficult to detect in the first place, even with modern technology. Objects near a planet's rings face a unique observational problem, sometimes described by researchers as trying to see a firefly next to a spotlight. Uranus's rings, along with the planet's cloud-covered surface, reflect a significant amount of light, especially in certain wavelengths. A tiny moon just 6 miles wide, sitting close to that bright ring system, gets overwhelmed by scattered light and glare, even through instruments capable of detecting incredibly faint objects elsewhere in the sky. This is precisely why one of the researchers involved in the discovery compared the challenge to staring into a car's headlights while trying to spot a small insect flying nearby. It's not that the object is impossible to see in principle. It's that everything around it is so much brighter that the contrast makes detection extraordinarily difficult, requiring both a highly sensitive instrument and a very deliberate, careful observing strategy specifically designed to filter out that glare. This is part of why the discovery took a full extended observing session rather than a routine imaging pass. The team behind the discovery didn't stumble onto this moon by accident during a general survey. They planned a deliberate, targeted set of long exposure images, specifically hoping to catch faint objects near Uranus's inner rings that earlier observations might have missed. That kind of intentional patient searching, paired with Webb's raw sensitivity, is what finally pulled a 6-mile object out of the glare that had hidden it from every previous mission and telescope, including Voyager 2's cameras in 1986 and decades of Hubble observations since. It's also worth pointing out just how small this discovery really is in the grand scheme of things, and yet how significant its implications are. A 10-kilometer object is barely larger than a modest asteroid. If this same object were floating freely somewhere in the asteroid belt between Mars and Jupiter, it likely wouldn't attract much attention at all. But because it's orbiting Uranus, tucked into a complex ancient system of rings and moons, its discovery carries real scientific weight. It adds a new data point to scientists' understanding of how small bodies form, move, and interact within a ring system. It raises fresh questions about whether the rings and inner moons form together, whether this moon is a leftover fragment from some ancient collision, or whether it represents ongoing, slow accumulation of ring material clumping together over immense timescales. Each of these explanations tells a different story about the violent, chaotic history that likely shaped the Uranus system billions of years ago, potentially tied to whatever massive impact knocked the planet onto its side in the first place. Stepping back, it's easy to see why this story resonates with so many people, even those who don't follow space news closely. There's something deeply human about the idea that a place we thought we already explored, a place we physically sent a spacecraft to visit, can still hold secrets. It challenges the assumption that exploration is a one-time event, a box that gets checked once a mission is complete. Instead, it shows that our understanding of even relatively nearby worlds is still evolving, shaped as much by the tools we bring to the search as by the objects themselves. Every leap in telescope technology, from Hubble to Webb and whatever comes next, has the potential to rewrite small but meaningful pieces of what we thought we knew. 40 years ago, Voyager 2 gave us our first real look at Uranus. It was an incredible achievement for its time, and it laid the groundwork for everything scientists understand about the planet today. But it was never the finish line. It was a single, brief snapshot of an enormously complex system taken with the best technology available at the time, under conditions nobody at the time even realized were unusual. James Webb has now shown us, twice over, just how much that snapshot missed. A temporary radiation storm mistaken for the norm, and a tiny hidden moon that had been quietly orbiting the planet the entire time, sitting in the glare of the very rings Voyager 2 photographed. As telescopes keep improving, and as the push for a dedicated Uranus mission continues to grow louder within the scientific community, there's a good chance this won't be the last time we hear that Webb, or whatever comes after it, has found something that Voyager 2, for all its historic achievements, simply couldn't see.